to the organizers for the invitation to come to meet all of you here. And I'm slightly relieved, actually, when Pradeep just took the vote. There are reassuringly fewer economists than I feared, so in this room. And what I'm going to do, by instruction of the organizers, I just want to quickly take through a few things related to the science behind the economics of climate change adaptation we are going to discuss in the next few days. First of all, just to place the climate information, climate science within this adaptation decision-making context, the big picture. Why do we need them? What are they for? And then a little update on what is the latest in terms of how climate is going to change and how confident we are in those projections, which we need to work with for our economics analysis. And finally, a couple of messages to bear in mind as we dive in deeper and deeper into the discussion in the next few days. So this is just a quick recap of this is one of the frameworks. There were different types of frameworks we can think about climate change adaptation in terms of the different steps and different tasks it involves. We normally start with the assessments at the beginning to analyze what kind of risks there are using different projections. And then we do our planning, what to do with the risks we identified. And this essentially involves lots of economics analysis, as we would discuss different options and weighing up the costs and the benefits of each of them. And that's planning. And then once we have decided we want to pursue certain interventions, we implement them. And we do monitoring and evaluation to assess progress. And so in all of this, what does climate change information and climate science sit is really, it provides the kind of information to support all these activities. It entails analysis of observed trends, how climate has been changing around us. And then also we use different modeling techniques to project what's going to change in the future. So this is basically where the climate science sits in this whole adaptation process. And then what exactly kind of climate information we need to enable us to make plans and to implement and monitor and evaluating adaptation interventions. And again, this is very context specific. If we deal with different sectors, we deal with different decisions, questions, and the requirement for climate information is very different. So if we're dealing with new infrastructure, at the very beginning, we want to scope the potential risks. And then for this kind of task, we cost resolution, very broad brush climate projections may be sufficient. But again, if we want to start to design the engineering design of a certain infrastructure, the drainage, for example, we need a very high resolution site-specific climate information to enable that kind of design phase. And then going down to the list, we have different sector issues and different tasks, and then we require very different climate information, from very coarse resolution to very fine resolution, both spatially and temporally. And so again, the key question is we need to understand the context of our decision for adaptation. Okay, I will try. So now we come to the second part, what we know about climate change and how it's going to change and globally and regionally. I don't claim to have the really comprehensive and all that new information. What I have here is in my role as the member of the IPCC, the Intergovernmental Panel on Climate Change Task Group on data and the scenarios for climate impacts, impacts and climate analysis. So I'm involved, not firsthand, but in some way involved in this intergovernmental panel on climate change assessment process. And there are some, the first assessment report is underway, and I'm involved in the review and some of the expert meetings. So these are from that process, and I like to, first of all, to just give a overview of how these climate projections are produced. And in the past, it's always been economists, largely. They prescribe a set of global emissions and socioeconomic scenarios to describe how our socioeconomic system will evolve and develop the pathways into the future. And from that, we have energy consumption, we have technology evolution, we have essentially the emissions and the different socioeconomic assumptions, and prescribe different emission pathways. And then we feed that emissions of greenhouse gases into different climate models and make projections of global temperature, precipitation change, and then using different techniques to bring that global projection into regional scale, and then using different sectoral models to assess impacts on different sectors, water, agriculture, health, and then analyze the adaptation options. So this has been the sequential way of making projections about emissions and climate change and the impacts. And from the latest assessment process, the scientific community has come together to adopt a brand new approach, for better or worse. And this is, instead of starting from the socioeconomic pathways, we have a set of representative concentration pathways, meaning we don't start from assuming how our economy is going to develop and how our technology is going to evolve. We start with some representative concentrations of different greenhouse gases. And then the economists and other research communities can work towards these concentration levels in using different socioeconomic pathways. As if we need to come to Bangkok, people have different ways of getting here, either by plane, either by swimming or cycling. So there is a kind of intermediate station we can all arrive at by using different assumptions about emissions and socioeconomic development pathways. And basically to break this sequential linear approach to adopt a more flexible and integrated approach to projection and scenario development. And in this way, the the climate modeling community can work together with the socioeconomic science of climate change in parallel, and then feed the information into the impacts assessment community. So this is the overarching scenario process to go with the latest IPCC assessment report. And this is, so the central, the four main concentration pathways were going from the top, 8.5. This is 8.5 is a measurement of the radiative forcing of greenhouse gases into the atmosphere. I was told at the breakfast by Professor Manderson not to use equations, but I'm afraid there are lots of technical terms here. So radiative forcing going from 8.5 to down to this 3 PD, it's a peak and decline scenario, basically stabilizes at 2.6. This is the lowest concentration pathway. And spreading a very wide range, as we can see here. And so these RCP pathways, they are replacing the old SRAS, A1, A2, B1, B2 scenarios here. So this is a rough comparison of these two sets of scenarios. in terms of concentration of CO2 equivalent. So we can see from this graph the latest range of scenarios is wider compared with the previous SRES emissions scenarios. And so with this set of new concentration pathways, there were projections fitting into a very simple global climate model. We can get a set of projections of global temperature increase in relation to the different assumptions about greenhouse gas concentrations. And again, there's a little comparison with the previous SRES projections. And as we can see again, this is again showing the slightly wider range of temperature warming. In this is the end of the century, the last 10 years in the 21st century. And these are some numbers here. This is a medium projection out of a very large range of climate model outputs. We take the median projection, and then this is 66% range out of a ensemble of over 50 model runs for temperature. So the key message here is really the range of projections hasn't changed very much in terms of the global warming figures from the previous projections. And the wide range is as a result of the wide range of emission of CO2 concentration range adopted for this new round of assessment. So the headline conclusion was the new generation of projections has suggested quite similar results to those from the previous rounds of simulations, and particularly the patterns of change, if not the absolute magnitude of change. I'm going to skip this one. So this is again in a tabular format of the projections. This is surface atmosphere temperature, and this is total sea level rise. And this is towards the end of the century projections. Numbers in the square brackets were the range, the range of different model simulations, and this is a median figure. And these numbers are still being reviewed and subject to change with the assessment process. And as we can see here, all the temperature projection figures are attached with a high level of confidence. And what these global projections mean when we use different techniques to actually downscale the global projections into our region. And Asia Pacific is a very large region, and it's been break down into, sorry, this doesn't really include any Pacific islands and just the Asian region. We have 7 sub-regions here. And so this is just a, some scatter plots showing the December, January, February temperature increase with relation to, I think now the baseline has changed from 1966 to 2005. And if we add 0.6 degree, you will get a temperature warming in relation to pre-industrial level. And as we can see from these figures, and so this is winter and this is summer, and the winter warming is much more prominent than the summer temperature increase. And in terms of sub-regions, and we see North Asia will have the largest warming in the winter. And for the summer, they have the Central Asia seems to experience the most prolonged warming. And for both cases, I think it's Southeast Asia seems to be warming the least. And then this is a scatter plot for precipitation during the winter and the summer seasons. And again, we see North Asia experience the largest increase in winter rainfall. And for the summer season, Central Asia seems to have the largest increase. And interesting here, we can see West Asia is a little bit of a outlier here. According to the models, it will have from mid-century onwards, it will have some decrease in rainfall in West Asia. And this will have implications for more severe drought situations. So these are the really headline figures here from the latest round of climate model experiments. And those were the basic temperature precipitation increase change, but I think as practitioners, we are much more interested in extreme events. Seasonal change in temperature and rainfall is relatively easy to manage, and we are more worried about extreme events like torrential rains and devastating flood events, like we already talked about earlier this morning. So in addition to those seasonal slow onset events, we also have changes in some extreme weather events. And here is just an example of the monsoon rainfall. And this is for the summer season in South Asian monsoon region. We show different indices of the monsoon rainfall. As we can see here, the total rainfall during the season will increase, but there is also a drought risk because the number of intense dry days here is generally increasing, and the total rainfall is also increasing. So we have more rainfall, but they will come in much more intense events and producing drought conditions as well. So in addition to slow onset changes, we also have changes in extreme weather events. So how confident are we in these different projections? So in general, we have less confidence in near-term projections, and this is just a graph showing different sources of uncertainty in the climate projections. And in we have three major sources. One is the natural variability, because the climate system is inherently has some kind of random noise going on within the system. We can't be perfectly sure at any moment how it's going to change from one moment to the next. And in the near term, this part will be dominating the climate projections, the natural variability. We know weather has always been changing. This is the natural variability part. And then the second part is the emissions, how our development pathways will affect the greenhouse gases in the atmosphere. We already talked about earlier this morning. Our activities in the past has already determined the atmospheric greenhouse gas concentrations for the next 2-3 decades. So for the next 2-3 decades, we may have a relatively small amount of uncertainty related to how much greenhouse gases there will be in the atmosphere. But finally, we have model uncertainty. Different models, they describe the climate system in different ways. And so as we move progress with climate science, this uncertainty may also reduce or at least stabilize. So adding all these different layers of uncertainty together, we can see actually around the year 2030, 2035, we may have a lowest total uncertainty in our climate projections. But in the near term, because of the natural variability, we have much less confidence in projecting climate change. And we have much higher confidence in the patterns of change, lower confidence in the magnitude. We know temperature is increasing, but we know much less, exactly how much and where this increase will be. And then we are more confident in quantities relating to thermal indices like temperature, but we are less sure about the water cycle indices, precipitation, and soil moisture, and so on. Unfortunately, these things are often much more important than just think about temperature. Again, this is a big challenge in science. And we also have overall low confidence in predicting many aspects of the extreme events, the probability and the frequency and the magnitude. So a quick summary, although the climate science is constantly improving and the models are getting more and more sophisticated, but there are still considerable uncertainties in the projections from these different models, and particularly for the parameters we are more interested in, which will have much more implications for climate risks into the future. And while we talk about climate models, talk about the projections, we shouldn't forget about the basic observations, which I think for some of you, maybe from the planning ministry or finance ministry, you heard your colleagues from maybe the hydrometeorology service asking for budget and for enhanced investment in basic observational system. So this is just a little illustration how in most cases climate change impacts are assessed. When we talk about how climate change is going to affect the crop production, for example, we use the crop models to model a certain type of crops in, say, 2050. We actually use the actual temperature measurement. We use the soil moisture. We use the radiation. But what the climate models give us is this delta term, not this baseline, because the models are fundamentally, there are some bias. So normally we use the model outputs to derive this delta term, and then combine that with the locally observed baseline data to get this say temperature in a particular season in 2020 or 2050, and then feed that into the crop model to assess the impacts on crop yields. And the same with precipitation and other parameters. So we shouldn't forget about the importance of observation, and a lot of Met Service now suddenly realize the need to really enhance the efforts in ensuring good observations in the region. And we talked a lot about uncertainty already and the risks and uncertainties. And as we can see, no matter how much progress we make in terms of climate science, in terms of improving climate models, and the natural variability part will still be there, and we will still have to live with uncertainties. So in this kind of situations, the good practice is to promote robust decision-making and flexible management. And in other words, we think about no regret or low regret adaptation options, particularly if we aim for poverty reduction. We talk about inclusive growth. So there are some opportunities there. And then we also need to bear in mind that when we try to interpret and communicate results from economic analysis, we need to consider, amongst the other things, the underlying robustness of climate information being used in such analysis. A sophisticated chef may be only able to do so much if the ingredients are not great. You may have very advanced cooking techniques, and you may have very advanced presentational skills, but the raw material, the ingredients were not great, so the results cannot be That's great. So we need to think about the underlying climate projections and to see really how robust it is for a particular location for the analysis. And finally, we need to again bear in mind the context of the analysis. If we are only talk about the very macro level agroeconomics, we may have to, we may use a kind of temperature elasticity to think about the economic implications of a certain degree of temperature change. In that case, maybe very broad scale temperature projection will be sufficient. But if you are designing your water supply system and trying to work out the sensible way of providing basic services, the requirement for climate information will be a lot higher. So we need to bear in mind the context of the analysis and also the scale of the amount of time and the resources we allocate to actually develop this climate information. If a project only has 8 months to analysis, a piece of economic analysis only has about 8 months to complete, and you spend 6 months trying to develop very fancy and sophisticated climate information, is probably not the most intelligent thing to do. So need to be proportionate to the scope of the overall analysis. With that, I will stop here. I think in the spirit of promoting more engaged debate and interaction, I will stop here, and I'm sure there are lots of questions.